Welcome back everyone. In this lecture we will actually classify all finite dimensional irreducible representations of sl2c. So we will begin with recalling some important facts about the representations of sl2c. So we start with let us say finite dimensional representation V of sl2c, finite dimensional representation of sl2c. So then we can talk about eigenspaces corresponding to the action of H. Okay, so we are interested in H action on capital V. Okay, so recall that eigenspaces of H, they are called weight spaces. Okay, H eigenspaces are called weight spaces of V. So in particularly for A in C, we can define VA, which is the eigenspace corresponding to A. So that is by definition those vector in capital V such that HV is actually given to be AV. So here we still do not know whether H acts diagonally on V or anything, but later we will prove that. Okay, H always acts diagonally on given any finite dimensional representation of sl2c. So this is the fact which will be proved later. H acts diagonally on any finite dimensional representation of sl2c. So we are actually suppressing the notation. So by representation we mean a map from sl2 of C to GL of V. So that map phi is actually suppressed. We are just writing H dot V for that phi of HV. Okay, this is the notation that we are using. So if VA is non-zero, so then it is called eigenspace. So that is also like called weight space in this setting. And for such VA, we call this A to be, which is eigenvalue weight of capital V. Okay. So these are all the notation that we will be using. So recall that what is highest weight space and highest weight vector. So we say a weight vector as highest weight vector or sometimes called maximal vector. So this is the terminology actually Humphreys uses, maximal vector. So if it is actually weight vector, so HV acts as AV. So of course highest weight vector of weight, let us say A in C, then HV is given to be AV and XV that should be killed. Okay, if these two conditions are satisfied, then we call that vector V. Okay, of course it is a non-zero vector. So this V is non-zero vector inside capital V. So this is called highest weight vector if this condition is satisfied. So we are interested in actually understanding what will be the submodule generated by this highest weight vector in given any finite dimensional representation of sl2c. But before that let us try to understand what happens with irreducible finite dimensional representation of sl2c. Okay, that case is somewhat easier to understand. So now onwards we actually just assume V to be finite dimensional irreducible representation of sl2c. Okay. So, when we actually analyze finite dimensional irreducible representation, we actually understand why these highest weight vectors and all they are important, how naturally it arises and so on. Okay. So, let us start with finite dimensional irreducible representation of sl2c, and then we will see the action of H on capital V and analyze what happens to it. Okay. So, as I already told, so we are expecting to have this H acts diagnostically on any finite dimensional representation. Okay. In order to prove that, first we need to prove that it happens in the irreducible case. Then you can use Weil's complete reducibility to say that H acts diagnostically on any finite dimensional representation. But one can also straight away prove that. We will actually try to give both proofs. Okay. So, now we take finite dimensional irreducible representation and see how one can prove H acts diagnostically on that. So, anyway, H treated as operator on V. So, H must have some eigenvalue. That operator corresponding to H must have some eigenvalue. Okay, that means it should have corresponding eigenvector as well. So, there exists A in C and non-zero vector W in capital V such that H W is given by A W. Okay. So, this is actually true for any operator. Okay. There exists always some eigenvalue. So, there is always some non-zero eigenvector corresponding to that eigenvalue. So, now it is a simple calculation to see that what happens to this x w. Okay, when I apply x on w, and then we can see that it has to have eigenvalue, either it is 0 or it will have eigenvalue actually a plus 2. So, let us compute this. So, recall, so what is Hx? Hx is nothing but Hx minus xh, which is given by 2x. So, in particularly Hx is given by 2x plus xh. So, if we compute xw and then h acting on that, then we can replace this by this formula. So, it becomes x of hw plus 2xw. Note that hw is aw. So, then it is becoming x aw plus 2xw. So, that means you can take a plus 2 outside and then xw outside. So, that means xw whatever it is going to lie inside a plus 2 eigenspace. So, this is the eigenspace or weight space corresponding to the eigenvalue or weight a plus 2. Okay. So, I am going to use weight and weight spaces and so on now onwards, because you are not familiar with the terminology. So, I am recalling again and again. So, eigenspaces for this particular operator are called weight spaces, and eigenvalues again will be called weights. So, now xw whatever it is going to be there in V a plus 2. Now, it is an easy exercise to see that if you apply x square w, that is going to lie in V a plus 4 and so on. So, in particularly if I apply x power any r w, that is going to lie in a V a plus 2 r. Okay. So, now note that if we are actually working with the finite dimensional irreducible representation, then given A, we can look at this A plus 2r, these numbers where r is going from 0 to infinity, they are all distinct numbers. So, in particularly not all this x or w will be 0. Okay, there will be some, only finitely many will be 0. So, that means there exists some k such that x power k w will be 0. So, we can choose smallest such k. Okay. So, choose smallest k such that x power k plus 1 is w is 0, but x power k w is non zero. Okay. So, this can be always done. So, now note that by replacing this x power k w as v, we get a highest weight vector, because h v becomes, so some lambda v, where lambda is given by a plus 2 k, and x v, which is x power k plus 1 w, which is 0. Okay. So, all we want is there exists weight vector which is killed by x. Okay. That is what we want. Okay. So, what is the use of this? You may be wondering. Okay. Suppose if I start with any non-zero vector in V, we know that by applying various powers of these basis elements, we will be able to generate this entire module capital V, okay, because V being irreducible. So, we can start with any u which is non-zero inside V. So, you apply various powers of this h, x and y. So, in particularly you apply like sigma x power some r1, sigma h power some r2, sigma y power some r3. Okay, you apply it on u, and then where r1, r2, r3 they are just some non-negative integers, where sigma is just the permutation on these 3 letters x, h and y. So, then if you take all possible vectors applied from obtained like this, and then take the span of that, then that is going to be definitely invariant under your sl2c. So, in particularly you will be getting actually sl2c submodule generated by u. So, but we know that V is being irreducible, this module has to be equal to capital V. So, this will become capital V. But you can see that this generating set is really huge generating set, because we have started with finite dimensional irreducible module. So, what we are actually proposed here some infinite, even though it is countably infinite, it is infinite generating set. Okay. So, it is not very good thing to do. So, we want to actually somewhat get the minimal generating set. Indeed, we are actually looking for nice basis of capital V. Okay. That is why we are first choosing this what is called maximal vector or highest weight vector. Okay, what to do with this? So, let us actually just try to understand what one can actually get from this. So, note that given this V, this is lying inside V lambda. So, now if we apply YV, where it can lie? So, it is again a simple calculation using the formula, the bracket HY, which is HY minus YH is equal to minus 2Y. So, in particularly HY is going to be YH minus 2y. So, in particular if I apply h on yv, so for this particular v which is non-zero, we have, so hyv is equal to yhv minus 2yv. So, in particularly this gives us actually hyv equal to hv is nothing but lambda v. So, lambda minus 2 yv. Okay. So, it tells you that if I apply yv, then it is actually going to lie inside v lambda minus 2. So, again one can apply various powers of y. So, you can see that y power some s v is going to lie inside v lambda minus 2 s. For various s, this lambda minus 2 s is going to be all distinct. So, that tells you that we can find smallest s such that y power s plus 1 v is 0. Okay. So, choose s in G plus such that y power s plus 1 v is 0, but y power s v is non-zero. So, this is because lambda minus 2 are all distinct. If all of them are eigenvalues, then that will imply that our space is infinite dimensional. So, because our space is finite dimensional, so we must find some smallest s such that this is y power s plus 1 is 0. So, now what we can do? So, we have these vectors v, y square v and so on up to y power s v. Okay, we take these vectors and then span these vectors. So, we will see that this is going to be entirely capital V. So, this is our climb. Okay. For example, let me do some small computation to convince you why this one can expect. For example, it is obvious that all these vectors are eigenvectors for the H action. So, in particularly they are stable under H action. Okay. The right hand side, let us call it V dash. So, it is immediate that V dash is stable under the y action and H action, because y is just going to increase the power and H is going to actually leave it constant multiple for when you apply it on any power of y v. So, in particularly it is going to be stable under both H and y. So, now we need to just see what happens to x. We know that x v is 0. So, what is happening with x y v? So, x y v, what we can do? We can use this formula, bracket x y is nothing but h. So, that means x y minus y x is actually h. Okay. If you use this formula, then x y v is nothing but y x v plus h v. Now, you can see that x v is being 0. So, this x of y v is becomes actually h v, but we know that h v is nothing but lambda v. So, this is going to give us lambda v. So, now let us do one more calculation, x y square v, what happens. So, for this again you can actually write it like this, x y y v. So, then this will becomes y x plus h applied on y v. So, that is going to give us y x y v plus h y v. Note that x y v is already lambda v. So, this is giving lambda y v plus, so this is going to be eigenvector corresponding to the eigenvalue lambda minus 2. So, this is lambda minus 2 v. So, that means when you take y square v, when you apply x on that, it is going to lie in the span of v and y v. That is the observation that we made. So, indeed we can actually make the general claim that if you take x power k v, x acting on y power k v, then this is going to lie inside the span of all these lower powers. Okay. So, that proves that the span of this v etc. y power s v is going to be x stable. So, in particularly v dash become sl2 submodule. So, since v is a finite dimensional irreducible representation, that forces that v dash being equal to v. That means we have this spanning set which consisting of the eigen vectors of H, namely v, y v etc. y power s v. Note that each eigenvalues are distinct. So, this spanning set must form a basis of capital V. So, let us verify this. This is again a very simple calculation. So, if we take x power y power k plus 1 v, let us use induction to prove that. Induction, we know that let us say x power y power k v is inside span of v etc. y power k minus 1 v. Okay. So, now we are calculating this. So, let us see, this is going to be xy times y power k v. So, that means yx y power k v plus h y power k v. So, note that, so this is going to lie inside, this entire thing is going to lie inside this span of this. So, that means this element going to lie inside span of y times v y v etc. y power k minus 1 v, and similarly this is there inside c y power k v, okay, because this is being eigenvector. So, that means, so this is going to lie inside entirely, this sum is going to lie inside the span of v y v etc. y power k v. So, this tells you that x applied on y power k plus 1 v is indeed inside span of v y v etc. y power k v. So, this tells that this v dash is indeed x stable as well. So, that means this v dash is sl2c submodule. So, that has to be equal to capital V. So, this proves that v is indeed span of all these eigenvectors. Okay. So, I guess we used S. Now, you can see that what are all the observation, this v, y v etc. y power s v, this form a basis for capital V, and each y power r v where r is coming from 0 to s are all weight vectors. So, corresponding to the weight, this corresponds to the weight lambda minus 2r. Okay. So, this has the weight lambda, this has weight lambda minus 2, this has weight lambda minus 2s. Okay. So, now here is the very important observation. So, in particularly if you set V I to be this y I power v, okay, for I greater than or equal to 0, okay, and then less than or equal, let us say yes. So, let us set this. So, then what happens, we have the following formulas. Okay. So, how h acts, h v I is going to give us lambda minus 2 I v I. Okay, it is clear. The second thing is how y acts, y v I is going to give us v I plus 1, because y just increases the power. Now, the third thing, x v I, that is the thing that we need to calculate. It is implicitly done in this calculation, but anyway let us do it very explicitly. What one can prove, this is exactly equal to I times lambda minus I plus 1 v I minus 1. So, basically these are all the formulas that we have seen in when we did the calculations in SM. There we actually normalized these vectors y I v as 1 divided by I factorial into y I v. Okay. So, slightly different formulas that we have seen, but anyway now we are doing it from scratch. Let us do this first. So, it is easy to prove first two. So, I will leave it as exercise. Now, what is there? We need to prove the third one. So, third one we prove it by induction. So, this is by induction. So, you take x v I plus 1. So, this is going to be x y v I, because v I plus 1 is y power I plus 1 v. So then you can replace this by yx vi plus the bracket xy vi, but bracket xy is h. So this is going to give you y I times lambda minus I plus 1 vi minus 1 plus lambda minus 2 I vi, because this is h. So now if you just rewrite y vi minus 1 is vi, so that comes out, then all these things just adds up, I into lambda minus I plus 1 plus lambda minus 2i. So this is what you are getting as coefficient. So now it is simple calculation to see that this is exactly equal to, so I lambda minus I into I plus 1, okay, minus lambda minus 2i. If you just calculate this is going to give you I plus 1 lambda minus I. Okay, so that means this is going to be I plus 1 lambda minus I vi. So this is the thing that we wanted to prove. If you put I plus 1 here, you get this formula. Okay, so this completes this calculation. So now what we are actually observing from this. So note that this lambda is chosen to be some weight vector which is actually highest weight. Okay, so because xv is being 0, so we are not able to add anything more. So note that here all the weights starting from lambda and then going down by 2 every time. Okay, it is kind of a string that starts from lambda and goes down by lambda minus 2, lambda minus 4 and so on, lambda minus 2s. But these calculations say something very important. So let's just look at this formula. So let me write it here. So this formula x vi is being I times lambda minus I plus 1 vi minus 1, and apparently it is true for all I greater than or equal to 0, no issue. So in particularly we can put I equal to r plus 1, sorry, s plus 1. So note that what is s? So we have chosen this vector v to be, so let us recall, y power s v is non-zero and y power s plus 1 v. So we have chosen this to be y power s plus 1 v is 0 and y power s v is non-zero. So this is how we have chosen. So that means if I put I equal to s plus 1, we get x v s plus 1 equal to s plus 1 times lambda minus s v s. So this is going to be what? This is going to be 0. Okay, because this is being 0, so this vector is also is 0. But note that Vs is non-zero. So Vs is being that y power sv. So this is non-zero. So that means this s plus 1 cannot be 0 because s being non-negative integer. So that forces that lambda minus s being 0. Okay. So this is indeed a striking fact. So even though we started lambda as arbitrary complex numbers, so the sl2 representation theory actually controls completely what could be the lambda. So indeed we are saying that lambda could be only s, and that must be a non-negative integer. Okay. So this is a very important observation that we make when we actually analyze this irreducible finite dimensional representation. But again, how one can associate this s with the actually with the irreducible representation v that we started with. Note that the dimension of v is nothing but s plus 1. So s can be obtained by dimension v minus 1. So let us actually write down all the observation that we made. Okay. So, indeed we can actually define this map from the set of all isomorphism classes of finite dimensional irreducible representations of sl2c to this Z plus. So, when we start with V, which is a finite dimensional irreducible representation, then we can see that we can send this map dimension V minus 1, then obviously it is well defined map, and this gives you one to one correspondence. Why? So, because dimension of V is well defined for the isomorphism class, there is no issue, and given any m here, we already constructed this irreducible representation Sm, which is the space of all homogeneous polynomials of degree m in two variable t comma u. So, we proved that sl2 naturally acts on that, and then that is indeed irreducible representation. Okay. So, because of this, this map is onto, and it is easy to see that this map is 1 to 1, because this number highest weight, that is why we are giving importance to the this S. So, this lambda indeed becomes S. Okay. So, now what are all the weights of this capital V? So, if dimension of V minus 1 is S, then V has this basis V, YV, etc., y power SV, where so V has eigenvalue S, YV has eigenvalue S minus 2, and so on, y power S minus 1, y power SV. So, this has eigenvalue minus S, and this has minus S plus 2. Okay. So, now it is not very hard to prove that. So, if dimension actually matches, so then the corresponding maximal eigenvalue, that is the highest weight, that will match. So, once the highest weight matches, then you can actually have this natural isomorphism from V to W by sending y power I V to y power I W. Okay. So, one can extend this linearly and then easily prove that this will be natural sl2 isomorphism between these two given irreducible representations V and W, which has same dimension. So, that proves that this map is indeed 1 to 1, and then it is on to, that gives bijective correspondence between finite dimensional irreducible representation of sl2c up to isomorphism and this non-negative integers. So, we are going to actually see some analogous picture when we actually go to SLN representation theory. So, of course, we have to replace this Z plus by some more little bit of sophisticated model. Okay. So, that is where all this semi-standard Young tableau and all will come, Young diagram or partitions will come. Okay. So, we will actually see in the future that how to classify all finite dimensional representation of SLN. Okay, I will stop here, and then we will actually continue with representation theory of SL2 in the next class. So, we want to prove complete reducibility of finite dimensional representations of SL2. Okay, thank you.